This video is the introduction to solving linear systems. The learning outcomes would be to use system of linear equations to solve application problems, add and subtract matrices, multiply matrices, write a system of linear equations as an augmented matrix, as well as solving system of linear equations using rref, which is going to be a function found on our graphing calculator. In a previous lesson, we learned that we could solve system of linear equations by graphing, by substitution, and by elimination. Now that we know how to solve systems of equations, now we're going to have application problems in which we can write them in terms of a system of equations. So there's a 6-step process when you have word problems, and the very first one is to read the problem. And the bigger thing is to understand what is being asked. So make sure you understand the question. The second thing is to assign variables. And I say a let statement. That's going to be when you state what does your x represent and what does your y represent. After you do that, you want to write a system of equations that represents your problem. When you write your systems of equation, it would look something like ax plus by is equal to c, and dx plus ey is equal to f, where a, b, c, d, e, and f are just some numbers. So you want to have that, and then now you can use any of those methods that we learned previously to solve. Today we're also going to cover a faster way of solving, so that might be something beneficial. The next thing you need to do is solve your system of equations. We've already discussed that you have graphing, you have substitution, you have elimination, and then if you want to, you can also use the rref that we're going to discuss later on. Then after you've solved, then you need to make sure that you state your answer in a complete sentence. And I ask that you do that so that it will remind you to make sure that your number has units. I believe my math lab will actually have the sentence probably written for you, and all you have to do is plug in your answer. But I want you to be able to understand that when you are doing this, you want to make sure you're clear about answering the question. And then the last thing I want you to do is to check your answer for reasonableness. That means that I know that you did the math correctly, so we're not checking it for accuracy, we're actually checking it to see if it makes sense. So like if you get something that says 5, and then you're like, oh wait a minute, the units are ounces, but the question was how much did the baby weigh when he was 1 year old, 5 ounces is really not logical in terms of an answer to that. So that's what I mean by checking for reasonableness. And you should have an example about using systems of equations to solve an application problem. So before I get into adding and subtracting matrices, let me do a little bit of background about matrices for you. A matrix is a rectangular array of numbers. So usually it's denoted with a capital letter. So let's say we have matrix A like this. And I'm going to create a matrix that has the elements of 3, -4, 5, and 2. So this matrix is what we call a 2 by 2 matrix, usually written like this. So sometimes you might see A with a 2 by 2 matrix to tell you the size of the matrix. So matrix A is a 2 by 2 matrix. The first number represents the number of rows, and then the second number represents the number of columns. So I just want to remind you that this is row 1, row 2, this is column 1, and this is column 2. So this is what we call the dimensions. This is a 2 by 2 matrix. Now if you want to add two matrices, then you need to make sure that they have the same dimensions. So if you want to add or subtract matrices, then you need to make sure you have the same dimensions. So if I wanted to add matrix A to some other matrix, we'll call it B, we will also know that matrix B needs to be a 2 by 2 matrix. And you should be able to see a video about adding and subtracting matrices. The only thing I'm going to say about subtraction, think of it as if I had A minus B, I can think of that as A plus a negative B. And so what you can do is give this negative to every element inside of matrix B, and then you're back to adding two matrices. So when you want to add matrices or subtract, then the corresponding elements are the ones that are added and subtracted. And I've already mentioned about thinking of subtraction as distributing the negative and adding it. So we're going to go on to multiplying matrices, and again I'm going to show you some information about that. So the one big thing you need to know about matrix multiplication is that the number of columns of the first matrix has to equal to the number of rows of the second matrix. So in other words, if I had matrix A, and matrix A is a 2 by 2 matrix, then when I multiply it times some other matrix, I'm going to call it C, and that matrix is a 2 by 1 matrix, then the answer is yes, I can multiply them because these two are equal to each other. This is the number of columns of the first matrix, and this is the number of rows of the second matrix. The cool thing is that once we multiply them, whatever my answer is, it will actually have the dimensions of the outside numbers. That would be a 2 by 1 matrix. So you can watch the video about example number 5, and you can make some determination about whether matrices can be multiplied or not. So the reason why I wanted to talk about matrix multiplication actually has to do with systems of equations. So first, let me just show you how multiplying matrices work. You will not be asked to multiply matrices just to determine whether they can or cannot be multiplied. But let me just show you this. Let's say we have matrix A, and matrix A is a 2 by 2 matrix, the one we mentioned before, 3, negative 4, 5, and 2. And let's say matrix C is a 2 by 1, and that is a 1, 6. So when we're multiplying, I want to multiply matrix A times matrix C. Then I will have 3, negative 4, 5, and 2. And I'm going to multiply it times 1 and 6. Now we've already mentioned this, that 2 by 2 times a 2 by 1 will actually give me, these two are equal, it will actually give me a 2 by 1. So an answer up here and a number right here. Two elements there. So let me show you how to multiply. Like, again, you don't have to know how to do this, but it kind of makes sense later. So what we're going to do is we're going to multiply the row times the column. And when I multiply, I'm going to get 3 times 1, that's this number times this one, plus negative 4 times 6. Negative 4 times 6. So when we do the math there, I get 3 plus a negative 24. So the answer is negative 21 right here. So if you want to find the second one, then I multiply by the second row and the same column that we had before. So this time it will be 5 times the 1, which is 5, plus 2 times the 6, which is 12, and my answer will be 17 here. So that's how you multiply matrices. Now, again, remember what I said, you don't have to know how to multiply matrices, but it will give you a better understanding about what systems of equations written in matrix form looks like. So for example, let's say we have matrix A, our same one that we had before, this one, and I have a matrix X, it's a capital X. And my matrix X is the two little elements of X comma Y. And we want to multiply AX. So when we do that, we're going to have 3, negative 4, 5, 2, and we're going to multiply it times little x and little y. And again, I showed you how to multiply, so I'm going to do it again. I'm going to multiply this row times this column. So I'm going to get 3 times x, which is 3x, plus negative 4 times y is negative 4y. And then I'm going to do the same thing with the second row. Multiply it 5 times x, which is 5x, plus 2 times y, which is 2y. Well, what if I told you AX was equal to some other matrix? Let's just say for fun it's equal to negative 21 and 17. Well, the elements are going to equal to each other. In other words, this one is going to equal to that. So that's going to give me 3x minus 4y is equal to negative 21. And the second element, 5x plus 2y, is going to equal to the second element of the other side of matrix. And now this looks like a system of equations. So what does that mean to us? That means that we can write any system of equations into a multiplication matrix form. So let's say we have 3x minus 4y is equal to 1, and 5x plus 2y is equal to 19. Well, we can write this part of 3, negative 4, 5, and 2 times our x and our y, and we can say that's equal to 1 and 19. But we can also write this as an augmented matrix to represent this system of equations. So notice this matrix here is made up of all the coefficients in front of our variables. So this one will be called a coefficient matrix. This one, if you think about it, is all the answers or the constants of our system. So I'm going to call that the answer column. So what happens is that we can rewrite our system of equations that we have here into multiplication form, as well as into what we call an augmented matrix, which is going to be 3, negative 4, as well as the 1 from the answer column, the 5, the 2, and the 19. So sometimes you might see it like this, or with a dashed line in the middle. It's to represent the coefficients of x and y and our answer column over here. Now, one of the things we have to be very careful about is that when we have our system of equation, it needs to be in standard form so that we know that these are representing the coefficient of x's, and these are representing the coefficients of y's, and these are what's on the other side of the equal sign in our system of equations. So this is going to be very important if we want to use rref in our graphing calculator. Coming back to our list of things to talk about in this video, we did talk about multiplying matrices. We determined what would happen if you multiply them. And I really said that you didn't need to know how to multiply matrices. The big thing is that you can see systems of equations in matrix form. And I also wanted to make sure that you knew what an augmented matrix was. And that you will be asked to do. For this last section about solving systems of linear equations using rref, it's a video that is not from the textbook and it's not created by me, but something that I found on the internet that I thought was very useful. To go along with this video, I have created a handout on how to enter matrices in a graphing calculator. It's part of the homework number for my notes. So make sure that you know how to use a graphing calculator. I showed you how to do that there. This one video will have several examples, and my job right now is to actually show you what happens when you're doing rref for matrices, and see how consistent and independent is going to look like, consistent dependence is going to look like, and how inconsistent systems are going to look like. And then we're going to interpret their solutions. And then the cool thing about rref is that you can actually use it for as big of a matrix that you need. So you can also use it for 3 equation systems. And again, this video will do that. So my job is to actually show you step number 3. So let me do that. So when you're solving using rref, these are the 3 things that can happen. So the very first thing I want to mention is this one right here. Remember what we talked about when we were doing multiplying matrices. This is our coefficient matrix, and we're going to multiply it times x and y. When we do that, we would have 1 times x, which is 1x, plus 0 times y, which is 0y, is equal to that first element. So what we find here is that 1x is equal to a, because remember 0y is still 0. And I do the bottom row, I would see 0 times x, which is 0x, plus 1y, that's 1 times y, is equal to the second number in our answer column, which would be b. And that will give us our value for y is equal to b. So our solution set here would be the point a comma b. So notice we could have seen that right here. Once you get what we call the identity matrix, the ones and the main diagonals and zeros everywhere else, then we know that this is going to be our answer. This is a consistent and independent system. When we look at the one in the middle, again, we see this is something unique. We get zeros all the way across, and again, if we were going to multiply it times our x and our y, that would be 0x plus 0y is equal to 0. And if we add these two, we end up with 0 is equal to 0. And we can see that this is a consistent and dependent system. Now the good news is you'll get some equation up here. If we multiply that times x and y, we would have 1 times x, which is 1x, plus a times y, and that's going to equal to the top number, which is b. So from here, depending if you want x arbitrary or y arbitrary, you solve for either x or y. So our equation is going to be x plus ay is equal to b. Because I can quickly solve for x, I'm going to have x is equal to negative ay plus b. So after I solved for x, I can see that it's dependent on y. So I'm going to have y arbitrary, and then instead of putting x, I'm going to put this expression. So negative ay plus b for our x value. So this is y arbitrary. Now I could have done this in x arbitrary. All that means is I would have to get my equation x plus ay is equal to b and solve for y. So I'm going to subtract x to both sides, and then I'm going to divide by a. So what we find out here is that it's dependent on x. So for x arbitrary, I would have some value for x, and my y would be this ugly expression. So our answer would be the point x comma negative x over a plus b over a. So you can see that this one is a consistent and dependent system. Last but not least would be this case over here. Well, notice again we have whatever equation we have at the top, but at the bottom here we have a very interesting row. Again, if I multiply that times x and y, I get 0x plus 0y is equal to whatever number is on the other side. And remember, I said c cannot equal to 0, because if it does, then we end up with the other scenario over there. So it's c is some other number. So think about it, that this might be adding up to 0 and c might equal to 3, and that contradicts reality. 0 does not equal to 3. So this one is actually an inconsistent system, and our solution set will be empty. So again, I just wanted to make sure that we've covered everything. Remember, for step number 4 here, you can use rref for any size of system of equations. So there should be an example of a 3-equation system. And that concludes this video.